Next talk is by Shuchi Chawla, simple pricing schemes for consumers with evolving values.
Okay, thanks Amit, and thanks everyone for coming. This is joint work with pretty much the same team as the last talk. So Anna and Nikhil over there and Balu Sivan. Okay, so one main message of my talk today is that uncertainty can be hard to model. So this is the optimization under uncertainty workshop. So the message fits in that way. And it makes sense for our community to think about approaches where we can come up with solutions that are robust to our modeling of this uncertainty. And this is very much along the lines of what Tim was talking about yesterday, but we'll apply it in a slightly different context. So this talk is about mechanism design, and mechanism design is driven by lack of knowledge or lack of information. So let's think of a simple setting where we have a seller selling an item, a few buyers show up, and the seller wants to maximize his revenue but doesn't know how much the buyers are willing to pay for the items. And the buyers may not know each other's preferences. And so the mechanism design problem is about trying to elicit this information so as to achieve the objective. And the seller has a lot of degrees of freedom by which he might obtain this information. So he might run an auction, might use randomness, sell items or bundles of items, or sell lotteries over items, and so on. So there's a lot of different things that this mechanism can do in order to obtain the information. And yet, in many different cases, we find that you don't actually need to use all of these different degrees of freedom in order to get a good approximation. So many times there are these posted price mechanisms that work really well, get a good approximation. One example is Anna's talk earlier, and Matt is going to talk about similar stuff later today. And these posted pricing mechanisms, despite their simplicity, or maybe because of their simplicity, tend to be pretty robust to changes in the prior, in the input, little changes to the model, whereas the optimal mechanism might not be so robust. So that's a nice property to have. Now, I'm going to go and add more uncertainty to the setup. So let's imagine that you have this seller and now a single buyer, but this buyer is going to show up every day and buy something from the seller. And as before, the seller doesn't know the buyer's value. In fact, the seller doesn't know what the buyer's value is going to be tomorrow or the day after, and so on. And here, the buyer may not know what his value is going to be tomorrow, the day after, and so on. And so the protocol that they engage in today, both the seller and the buyer are going to strategize depending on what their beliefs are about how the buyer's value and preferences are going to evolve in the future. Okay, so this brings in more degrees of freedom for the mechanism designer. You can do more interesting stuff. You have to be very careful in that in this setting, the buyer is now facing some risk as to what's going to happen in the future. And you have to make some assumption about how the buyer reacts to that risk. So the seller may not know whether the buyer is risk neutral or risk seeking or risk averse. And in fact, the buyer might not know himself. So if I offer you a lottery that pays you $10 with 50% probability, how much are you going to be willing to pay for it? $5, $4, $3? I'm sure everyone has a different answer for how they assess the value of such a lottery. And if it's a more complicated distribution, it's not easy for a buyer or an individual to assess for themselves how much this kind of risk is worth to them. And in fact, it's even harder to make decisions that are consistent across different kinds of lotteries. And so risk is something that's very tricky to model correctly. Okay, and so this is one way in which uncertainty creeps into the system. And the thrust of this talk is that in this kind of setting, it can be possible to design mechanisms, and again, these are going to be posted pricing type mechanisms that are robust to this sort of uncertainty about the behavior of the buyer. Okay, so that's the main message. Okay, so let me be more specific about the kind of problem that we study, and it's a stylized model. So we're going to imagine that the seller has an app to sell, and the buyer is going to use this app multiple times. And the buyer doesn't know how what his value for the app will be in perpetuity. Instead, his value could evolve, in fact, as a function of his experience with the app. So the buyer uses the app one day, enjoys the experience, his value goes up for the next use, and then the next day it's not quite as enjoyable, and the value goes down. After some time, the buyer may altogether tire of using the app, and so his value goes down to 0 and he stops using it. Okay, and one question that we might think about here is what is the item or the product that the seller is trying to sell? Is the seller selling unlimited use of the product or a single use of the product? What is the item that we want to price? Is it promise of future availability? Is it a membership type model? There's a huge number of different things that one might do here. Okay, so let's formalize all of this. And so for those of you who are not familiar with mechanism design, here's a quick introduction to how you might formalize this. So in a single shot setting, when you have the seller just has a single item to sell and the buyer has a value for this item, here's how a typical mechanism design protocol plays out. So the seller is going to learn the distribution for the buyer's value, and based on this, he's going to announce an allocation function and a payment function. And then the buyer is going to draw a value from this distribution. He's going to bid some amount in the mechanism. And then the seller is going to sell the item with probability, this function x applied at B and at price P of B. Okay? And the property that we want is if the buyer looks at his utility from this sale, so this utility is his value times the probability he got the item minus the price he had to pay, then these functions are picked in a manner that this utility is maximized by the buyer reporting his value truthfully. So it's maximized at D equals V. And subject to this constraint, IC here stands for incentive compatibility, we want to maximize the expected payment that the buyer makes. Okay? So what about the dynamic setting? Well, here again, so on the first day, the game plays out in pretty much the same way. The buyer draws a value from the distribution for the first day, reports a bid, and then the seller picks some allocation function, some payment function. Now, the next day, though, the buyer's value might be drawn from a distribution that depends on what happened on the first day. And again, he reports a bid, and this time the seller again picks some X2 and P2, and this again depends on everything that the seller has seen so far. Okay, and likewise on day I, all of these V's and X's and P's depend on everything that's happened in the past. Okay. And what are the properties that this mechanism should satisfy? So it again needs to satisfy some kind of incentive constraint. So let's think of the buyer's utility on the ith day. This is this function here. And so the seller's constraint should be that if the buyer looks at his total utility from that accrues over time, then this should be maximized. Yeah.
Is there a PIXI or the buyer pays irrespective of getting the item?
It depends on how you define the price, but let's say that the buyer here pays irrespective of the, yeah. Okay. Yeah. And then the seller again wants to maximize the payment that he gets from the system. Okay, so this is one way of formalizing this problem. And some of you might have noticed that I sneaked in an assumption here without stating it, which is that the buyer is risk neutral. So as soon as I put an expectation here, there's a risk neutrality assumption that I made. Did you have a question?
So, does the seller know that all these FIs across time, even at time 0, or do?
Okay, so good question. So we're actually not going to closely look at this model, but this is the assumption that goes into this sort of work. If you start to write down a model, you assume you know everything about how the value evolves, how the process evolves, and then and just in order to be able to mathematically formalize this, you make assumptions of this sort, that the buyer is risk neutral, or you make a different assumption, but you write down a precise mathematical model of what that is. Okay, and this is there's a ton of work on these dynamic settings, and this is the sort of approach that this work takes. In fact, some of this by people that are present in the audience. It's beautiful work, and these are really challenging problems. They're non-trivial even in the simplest settings. So for example, even if the values on different days are independent, because of this revelation of information that's happening over time, the mechanism design problem becomes complicated. And one needs to make these strong assumptions in order to obtain any sorts of results, such as that the buyer is risk neutral, and it requires the seller and or the buyer to solve these complicated MDPs in order to be able to solve this problem. So it's really not a desirable state of affairs. And what might we ask from a satisfying solution to this problem? Well, hopefully it's simple to compute and implement, which the previous kind of model is not. You'd want it to be detail-free in the sense that we don't have to make very fine-grained assumptions about exactly how the value evolves, for example, among other things. Hopefully, not very many assumptions about the buyer's attitude towards risk. And you should still be able to approximate optimal revenue. So I've just put down, what would be the best case scenario here. And the message of this work is that under a very stylized model, it is actually possible to achieve all of these. Okay, and I'll show you the model where it's possible to achieve this. Okay. Okay. So that's sort of the very high level picture. Now let me say a few words about the specific model. So we're going to assume that, so again, this is the App Store setting. The buyer is going to buy an app to use and then use it for some amount of time. We'll assume that there's some distribution for the buyer's initial value, and the value is always bounded within some range. And the value is going to evolve by having a random shock added to it at every step. And we're going to assume that the value always stays bounded, so it never goes beyond 1. And once it reaches 0, it gets absorbed at 0. That's like saying the buyer loses interest in this product. Okay? Okay, and what is our mechanism going to do? We're going to, in the interest of simplicity, we're going to assume that the seller announces a per usage price for this product. And this price could look like, some sort of varying price over time. Okay? And so the seller specifies precisely how much the buyer needs to pay for every subsequent use of the product ahead of time. And then we're gonna, so we need to make some assumption about how the buyer reacts to this price. So we're gonna assume that the buyer buys the product as long as his value stays above the price announced for that particular usage. Okay, so recall that the value evolves stochastically as long as the value at that point of time is above the price announced for that point of time, the buyer is going to buy. Once the value goes below this price, we don't make any further assumptions about what the buyer might do. He might continue to buy or not, but we're not going to account for that, for the revenue from that. So we call the total revenue accrued up to this point as the seller's risk-robust revenue. Okay, and this is what we want to analyze. Yeah.
Later, the value will be above the price. He returned to buy.
We still won't account for the revenue from that. Yeah. Okay. And so, what do we want to compare this against? So we're going to give all kinds of advantage to the optimal solution here. So we're going to assume that the optimal solution knows what the starting value is, and so the optimal solution, so the optimal mechanism could potentially look at the total value that the buyer could accrue over the entire process and charge the buyer exactly that. Okay, and you can imagine in some state of the world where this might make sense. And so we call this the cumulative value of the buyer, and this is going to be what we compare our risk-robust revenue against. Okay, so pictorially, the blue area here is the risk-robust revenue that this pricing achieved, and if we let the value evolve until it goes all the way down to 0, then the red shaded area here is the buyer's cumulative value, and we want to come up with a pricing where the blue approximates the red. Okay, so that's the goal. Yeah. I'm going to come to assumptions that go into the theorem. Yeah. Okay. So this is what we want to do. Blue approximates the red. We want to come up with this pricing. Now, pictorially here, this seems like somewhat of a daunting task. And let me give you an example where a very simple pricing is not going to achieve a good approximation here. So let's suppose that the buyer's value evolves according to a simple random walk with some fixed step size. And we're going to, so let's let V be this initial value. And we're going to consider this class of pricings where the seller just announces a constant price P for the item for every time step. And observe here that the buyer's cumulative value is going to look like it's going to be linear in V and 1 over the square of the step size. So you can, this is easy to compute by writing down a series of equations. This is a simple random walk. And so you solve these, you get V over delta squared for the cumulative value. On the other hand, if we look at how long this mechanism accrues this risk-robust revenue, this depends on how long this random walk takes to hit this price P. And so we can analyze that because this is a simple random walk. There is reflection at 1 happening, but we can, unfold the random walk around 1. Think of this as a random walk between 0 and 2, and then ask how long does it take for this random walk starting at V to hit P or 2 minus P. And that's a simple expression. It's basically this length times this length divided by delta squared. So about V minus P over delta squared is what it turns out to be. And so the risk-robust revenue is basically P times this. Okay? And now even if we knew what the starting value V was, the best we can do is to set P to be, let's say, V over 2, and this gives us risk-robust revenue, that's V squared over delta squared. And you can see that there's a gap between the cumulative value and the risk-robust revenue, and this depends on the starting value V. If V is tiny, then this gap is large. Okay? So we don't want that. Okay, so what this example shows is that even for a simple random walk, if your solution is just a constant price, then you cannot hope to achieve the kind of theorem that I want to achieve. Okay? Okay, so what can we do then? So we're going to show that you don't need to make things too much more complicated beyond just a single price. So here's what the solution looks like. We're going to offer the item for free to the buyer for the first few time periods, and then we're going to charge a fixed price. Okay, so this is just a free trial period where the buyer gets to try the item and see how much he likes it, and then there's a fixed price thereon. Okay, and we're going to analyze this under a model where the value evolution is a martingale. Let me go through this model in some more detail. So I already mentioned that the value is bounded between 0 and 1, and there's absorption at 0. And then this follows the martingale property. And we make the assumption that the step size for this martingale is bounded. So epsilon is a bound on the step size at every step. And it also has some minimum variance. Okay, and for our result, all of these turn out to be essential.
So how is it bounded above by 1?
How are the values bounded above by 1?
Yeah, because it's a martingale. So if it
Yes, so the martingale property holds. So the martingale property holds whenever the value is strictly between 0 and 1, but not at 1. At 1, it bounces back.
So when it gets closer to 1, it takes smaller steps then?
That's right. So there's, we need to, so you're absolutely right that this step size needs to be relaxed when the value is very close to 1. So there are some more the technical things that go into it when you get very close to 1. Yeah.
There is just small typo. The expectation of delta t condition here should be 0, right?
Oh, yes. Yeah, this was supposed to be Vt plus 1. Yes. Yeah, thanks. Yeah. So it is a martingale. This one doesn't look like it, but yeah. Okay, so what is the theorem? So the theorem is that if you have a martingale process with these epsilon and delta values, so there's an upper bound and lower bound on the step size, then we can come up with this kind of pricing where we have a free trial period and then a fixed price that obtains an approximation to the cumulative value that depends on the ratio of epsilon and delta. And furthermore, the C and T here depends only on epsilon and delta, and it suffices to have estimates for these quantities. And we don't need to know anything else about the martingale process at all. Okay, so in particular, the value evolution can depend on the entire history, and we don't need to know any details about that. As long as we have estimates for epsilon and delta, we can get this approximation. Yeah.
So if we don't know epsilon and delta, is there any way that we can find the threshold by just like...
I don't know.
Okay.
I don't know. You need to know this to be able to, so let me show you the proof and it'll become clear a little bit.
So at what time do you determine the value PT?
At the very beginning. So we announce this entire pricing at the beginning. Okay, and observe that we are saying nothing here about what the initial value distribution is. So the initial value distribution can be completely arbitrary. Okay, so a couple of comments before I show you the proof really quickly. So, so even when this initial value is known, a sort of buy it now approach where you try to price usage at the very beginning is not going to get this sort of theorem. What this pricing lets us do is to price discriminate while still being NV-free. And it also gets a larger market share than a kind of mechanism that tries to price the product in the beginning. So I'll go very quickly past this. Yeah.
Just to get the intuition, the idea of the trial period is to make the value random instead of deterministic. That's like the high intuition behind the...
Yeah, the idea of the free trial period is that even if you start with a very low value, there is still a small chance that it's going to pick up. You're going to start liking the item, and it lets this do that. So let me show you a very quick proof for the simple random walk, and then some intuition for the general martingale case. And in the simple random walk, the idea is basically that we want the free trial period to be long enough so that this value that starts out really low has a good chance of climbing up to a high value before we start charging the buyer anything at all. Okay, so just to put some numbers here, recall from these are some easy facts about random walks. If you look at the probability that this random walk starting at a value of v is going to reach 1 before it reaches 0, this is exactly v. Okay, this is just a simple consequence of optional stopping. And then we can also compute the expected time taken to reach this high value, conditioned on the fact that it reaches this high value. And this turns out to depend on the step size. So it looks something like constant times 1 over delta squared. And then once it climbs up to this high point, the time that it takes to get down to a price of C is also about 1 over delta squared. Okay? So the thing we want to achieve from our pricing is that we want this event to happen before we start charging the agent. Okay? And then, but we want it to happen, but we want to start charging the agent early enough so that we have enough time to make some revenue. Okay? And there's a choice for this capital T that allows us to do that. So if we set T to some constant times 1 over delta squared and C to some constant, then there's a constant probability that if the value indeed climbs up to 1, then we're going to be able to charge the buyer for long enough to be able to make some revenue. Okay, so we put all of that together. We get that with probability omega of v, we get revenue constant over delta squared. And recall that the cumulative value here was v over delta squared, and so these are within constant factors. Okay, so that's a very rough argument for what happens in the simple random walk case. Okay. Now, what goes wrong with this proof for a general martingale is that when this value is climbing up, this might happen rather slowly. Okay, now the martingale, recall, has an upper and lower bound on its step size, and these could be quite different. And so it could happen that it climbs up to a high value very, very slowly, but on its way down, it's really fast. Okay, so we're trying to capture revenue from this really short interval, the high value to down to the price. And this is a short interval, and where this interval begins has a large variance. Okay, so it's really tricky to set a length for this free trial period in just the right way so that we capture the revenue from that short interval. Okay, so that's the tricky part with a general martingale. But the way we do it is, instead of thinking about, instead of setting it up so that the value climbs all the way to 1 before the free trial period ends, we look at some smaller value that's above the price that we're going to charge. But then we set this, we look at this sort of checkpoint in such a way that this checkpoint is achieved quickly, okay? And so this time around, so we may be quick here, we're going to look at 3 different events. So we're going to look at this initial part of the process where we're trying to argue that with some probability, the value is going to climb to this checkpoint W before the free trial period ends. And then we're going to look at this next stage where we say that there's a good probability that this value will keep climbing all the way up to 1 before it goes down to the price C. And then we're going to exploit this third phase of the process where the value now takes some time to go down to all the way to the price. Okay, so we break up the analysis into these three components, and again, much of this analysis is based on the optional stopping theorem and analyzing just the right functions of this martingale process. So it's all very elementary, and it works out nicely. And we get this property that all of these good events, these checkpoints, are achieved with probability that's linear in V, and then we get revenue that looks like delta over epsilon cubed with the right choice of parameters. And again, the Bayer's cumulative value is V over delta squared, and so the ratio then becomes this function of delta over epsilon. Okay, so that's very quickly what the argument looks like. So let me just conclude saying that I showed you a very stylized model of this dynamic mechanism design problem. The high-level thing to take from this is that in many such complicated settings, you can find simple mechanisms that are not only approximately optimal, but also robust to knowledge about, robust to modeling decisions or information about the input. And in this case, it's also robust to the Bayer's risk attitude. And I want to leave you with two thoughts. One is that we should value this kind of robustness, I think. And the second is that there's this perplexing thing in mechanism design that we see many different settings where these posted price mechanisms perform really well, and it's a little bit perplexing in that we don't need to use all of the different degrees of freedom that we have in in this optimization problem, and yet we end up doing so well. So I wonder if there's some meta theorem here for why these posted price mechanisms work so well. So that's it. Thank you.
So you showed that if the jumps are independent, basically we have random walk, we get constant, right? Constant approximation. And then when you relax
That's right.
martingale, you get like delta probably 1 over epsilon. So do you know to what extent can you...
So we can also show that if the jumps are independent of the current value. So the step sizes are all different over time, and the distributions of the shocks could be different, but are independent of the of VT. Then you can shave off a delta over epsilon factor, but I don't know how to do better.
That's basically the random walk, right?
No. The random walk, the step size is the same throughout time.
Okay.
So you can have different step size, and also it doesn't have to be plus delta or minus delta. It can be a totally different distribution with mean 0. But as long as it's independent of VT, then you can shave off another factor, so you can do that.
So do you know to what extent you can relax the stochastic process such that you still get something meaningful?
So I'm not sure that the strict martingale condition is really necessary to achieve this, but we don't know of techniques to really go beyond that. Did you have a question?
It's sort of a follow-up to Rod's question. Do you have any example where it satisfies the martingale condition, but where...
the lower bound and upper bound on the step size, is that?
Where the simple type of pricing, where it's try it for free and then pay a constant price, you cannot achieve a constant approximation. Like
you mean independent of the parameters?
Faster than epsilon, and you can actually prove that this simple type of pricing in that regime is insufficient.
So we do have some interesting examples. I can tell you more offline. Yeah, but the lower bound and upper bound on the process is necessary, without which we cannot get results. So in some sense, the ratio, the approximation also necessarily depends on these lower and upper bounds. Yeah.
That was my question. Great.
Okay. Thanks.